You pick up your phone, tap out a message, hit send. Or maybe you dial a number, hear that familiar ringtone. It feels instant, almost magical, right?
Yeah, it really does.
But what incredible dance of technology actually happens the moment you initiate that communication? What complex systems, spring to life behind the scenes?
It's a world away from simple. It's an intricate ballet of physics, engineering, and complex protocols working in concert. Really quite amazing when you think about it.
And that hidden world is precisely what we're diving into today. We've taken a substantial stack of your sources, articles, research notes, diagrams, all focused on peeling back the layers of telecommunications and advanced communications.
Right. And our mission really is to cut through the complexity. We're here to unpack this material, distill the most important insights, maybe find those surprising nuggets.
Yeah, and give you the essential shortcuts to truly understanding this foundational field.
Exactly.
Forget information overload. This is about getting well-informed quickly. We're going to journey from the fundamental ways a signal physically travels.
Explore the challenges it faces.
Understand how vast networks are built and uncover the ingenious ways information is shared and switched, all the way up to the modern vision of packet-based communication.
Sounds like a plan. So let's start at the beginning. At its heart, telecommunications is simply the exchange of information over significant distances using electronic means.
Right. Voice, data, video.
Whether that's voice, data, or video. Exactly.
And it's not just one-to-one anymore. It's often many points communicating across a network.
Absolutely. And a telecommunication network is that collection of devices, nodes, interconnected by links to exchange messages.
And those links can be physical, like cables, or entirely wireless.
That's right. We interact with these networks every day. The phone network, the PSTN, the internet, your cellular service, satellite comms.
All examples.
Yeah. The physical link itself is the transmission medium, what carries the information from source to destination. Think of it as the road the signal travels on.
And those roads come in two main types, guided and unguided. Guided media provide a physical path, like the copper in twisted pair or coaxial cable, or the glass in fiber optic cable.
The signal is literally guided along the medium.
Right.
Unguided media, on the other hand, transport signals as electromagnetic waves through space without a physical conductor. That's your wireless communication, radio waves, microwaves, infrared.
And these media aren't perfect, are they? They have properties that define how they perform, like bandwidth.
Right. Bandwidth, the capacity to carry information, and also things that degrade the signal over distance, like attenuation, signal loss.
And how long it takes for the signal to travel, that's propagation delay.
Exactly. Now, for higher frequencies or specialized applications where the electromagnetic wave properties are critical, we use transmission lines. These aren't just passive wire.
Like the ones you'd see carrying signals between complex equipment. They're designed, really carefully.
Precisely. They're structured specifically to conduct those waves efficiently, preventing reflections and power loss. You find them in things like telephone trunk lines, high-speed data connections, or even within computer buses.
What's the big deal about reflections, though? Why worry about that?
Well, reflected power means wasted power, and it causes signal distortion. It messes things up. That's why impedance matching is so crucial for transmission lines. The load impedance at the end needs to equal the line's characteristic impedance, often called Z0.
So if it's matched, the signal just gets absorbed by the load. No bounce back.
Yes, ideally. To the source, a perfectly matched line looks infinitely long because no signal bounces back. Z itself is a property of the line's physical and electrical characteristics.
Like its resistance and inductance.
Basically, yeah. How much series impedance, resistance, and inductance it has relative to its shunt admittance, capacitance, and conductance. For a simplified lossless line, 0 is just the square root of L over C inductance per unit length divided by capacitance per unit length.
Okay, and how do we measure how bad the reflection is? Is there a metric?
Yep, that's return loss. It tells you how much of the signal energy is reflected back towards the source. A higher return loss value is better.
Because it means less reflection.
Exactly. Less reflection, a closer impedance match. An infinite return loss signifies a perfect match, which is the ideal goal.
Okay, let's apply this. Our old familiar phone line from the house to the local exchange, the subscriber loop that's typically two-wire, right?
That's right. Both directions of the conversation, sending and receiving, use the same pair of wire.
But in the network itself, connecting exchanges or carrying signals long distance, systems often use four-wire transmission.
Correct. Separate paths for sending and receiving. 2 wires transmit, 2 wires receive. much cleaner separation.
So you need something to connect the two-wire house line to the four-wire network trunk. A bridge, sort of.
That's the hybrid transformer circuit at the exchange. Its job is to split the incoming four-wire signal to go to the two-wire loop and combine the two-wire signal from the loop to go back onto the four-wire receive path. It's essentially a power splitter.
Okay. And the challenge? What's the tricky part?
Impedance matching again. If the impedance of that two-wire line isn't perfectly matched by a balancing network within the hybrid circuit,
Then signal bounces back.
some of the signal going to the two-wire line will bounce back and leak onto the four-wire receive path. And that's the origin of echo.
Ah, so the echo we sometimes hear is often a consequence of imperfect impedance matching right there at that hybrid, connecting the two-wire loop to the four-wire trunk.
Exactly right. Subscriber loops vary wildly in length, condition, you name it, makes perfect matching consistently very difficult.
And this leads us directly into signal impairments, basically. Anything that messes with the signal as it travels.
Like the signal getting weaker, which is attenuation.
And distortion, like delay distortion, where different parts of the signal arrive at different times, smearing it out.
Yeah, that can really degrade quality.
And of course, the ubiquitous problem, noise.
Ugh. Noise. It's random, unwanted electrical energy added to the signal. It's always present to some degree.
What kinds are there?
Well, you've got thermal noise just from electron movement, induced noise from external sources like motors, crosstalk from interference between adjacent lines.
Like hearing another faint conversation.
That's crosstalk. And then impulse noise, sudden spikes from things like power surges or lightning strikes. Nasty stuff.
How do we quantify the impact of all this degradation, especially noise? How bad is it?
The signal-to-noise ratio, or SNR, it's a fundamental measure of signal quality, simply the ratio of the signal power to the noise power.
So higher is better?
Much better. A higher SNR means the signal is stronger relative to the noise, resulting in better quality. If your signal is, say, 10 milliwatts and the noise is 1 microwatt, that's an SNR of 10,000.
Wow. And we often express this in decibels, right? For convenience.
Yeah, using the log scale.
Yeah.
SNR in dB is 10 times log base 10 of that power ratio, so 10,000 becomes 40 dBs.
Okay. You mentioned echo earlier, linked to the hybrid. That's another impairment, right?
Yeah.
A big one for voice.
It is, and a significant one for quality of service, QoS. It's feedback the transmitted signal bouncing back into the receiver path. As we discussed, often due to that impedance mismatch at the two-wire to four-wire hybrid.
And singing. What's that?
Singing is basically echo gone wild. It's an extreme self-sustaining oscillation caused by positive feedback when the echo is severe, often at a specific frequency where the circuit losses happen to be very low. It's like uncontrolled howling.
Right. Okay. And controlling these involves trying to fix the impedance match, maybe adding some loss, or just turning down the amplifier gain.
Precisely. Those are the main tools to combat echo and prevent singing.
Okay, let's think about network efficiency now. The roads we're using the transmission media, they often have far more capacity than a single user needs, right?
Right.
Like a whole fiber optic cable for just one phone call. Seems wasteful.
Incredibly wasteful. Absolutely. That's where multiplexing comes in. It's a core technique for bandwidth utilization, basically, sharing the medium efficiently.
So the idea is to send multiple independent signals simultaneously over a single shared path, like multiple lanes on a highway.
Exactly. At the transmitting end, a multiplexer, or MUX, combines the signals. At the receiving end, a demultiplexer, DEMUX, separates them back out. It maximizes network resource use and saves a huge amount on physical cabling costs.
And two classic ways to do this are frequency division multiplexing, FDM, and time division multiplexing, TDM. What's FDM?
FDM divides the bandwidth of the medium into smaller, non-overlapping frequency bands or channels. Each signal gets its own dedicated slice of the frequency spectrum.
Like tuning into different radio stations on the same airways. Each has its own frequency.
Perfect analogy. Each station broadcasts on a different frequency. FDM is common in broadcasting and can carry analog signals or digital signals that have been modulated onto analog carriers first.
What are the downsides? Are there any?
Well, you need guard bands, little bits of empty frequency space between channels to prevent interference, and that wastes some bandwidth. Plus, it requires relatively complex filtering and modulation hardware for each separate channel, though modern versions like OFDM, used in things like 4G, are much more bandwidth efficient.
Okay. And TDM, how does that work?
Time division multiplexing divides access to the medium by time. The medium's full capacity is allocated to each signal, but only in rapid sequence for a brief time slot. This is primarily used for digital signals.
So each signal gets a turn really fast.
Exactly. In synchronous TDM, each input line gets a fixed time slot in a repeating frame structure, even if it has nothing to send at that moment.
Ah, so that could be inefficient if lines are often idle?
It can be simple to implement, but potentially wasteful with empty slots. Statistical TDM, sometimes called asynchronous TDM, is smarter about it. It only allocates time slots to inputs that actually have data waiting to be sent.
So it dynamically shares the capacity based on need.
Right, it improves efficiency, especially when traffic is bursty, meaning it comes in fits and starts.
And the phone network's digital hierarchy, like those T1 or E1 lines we hear about, that's built on TDM.
Correct. A T1 carrier combines 24 digital voice channels using TDM into a 1.544 MEDS stream, while an E1 combines 30 voice channels into a 2.048 MEDS stream. It clearly shows how TDM is used to aggregate many lower speed signals onto a single higher speed link.
Okay, so we understand how signals travel
Yeah.
and how to share the path. How do these paths connect into large-scale networks? What makes a network?
That's data communication. At its core, you have a message, a sender, a receiver, a transmission medium we just talked about, and critically, a protocol.
The protocol being the set of rules.
Exactly. The set of rules defining how that communication actually happens. Everyone has to agree on the rules.
And effective data communication needs.
Sure.
Well, it needs to be delivered to the right place, be accurate, and arrive on time.
Yeah.
Right. Especially for interactive stuff like video calls.
Absolutely. Delivery, accuracy, timeliness, those are key. The flow of data itself can be simplex.
One way, like a keyboard to a screen.
Right. Or half duplex, one way at a time, like a walkie-talkie.
Push to talk, release to listen.
Or full duplex, both ways simultaneously, like a normal telephone call.
And network structure involves the physical connections point-to-point between just two devices or multi-point where one transmission goes to many recipients.
Correct. And also the physical topology, the geometric layout of how things are connected.
Like the shape, mesh, star, bus, ring.
Right, those configurations. Each has its own trade-offs in terms of reliability, cost, how easy it is to add new devices, and overall performance.
Networks are also categorized by scale. LANs, WANs, and MANs.
Yep. Local area networks, LANs, are small, usually privately owned networks, linking devices in a confined area like an office building or a campus, often for sharing resources like printers or servers. Wireless LANs are everywhere now.
Then WANs. Wide area.
Wide area networks, WANs, span much larger geographic areas, like a country or even a continent, enabling long-distance communication. The Internet itself is a massive, complex WAN built from many interconnected networks. Businesses also use WANs to connect distant offices.
And MANs fill the gap. Metropolitan area networks.
Exactly. MANs typically cover a city or a large part of a city. They often provide high-speed connectivity, maybe connecting LANs together. Cable TV networks or DSL infrastructure could be examples of MANs.
And the internet ties it all together somehow.
The internet really is the quintessential network of networks. It's a global interconnection using the TCP/IP protocol suite, constantly evolving, connecting vast numbers of devices and smaller networks, usually through internet service providers, ISPs.
Okay, when you're connecting devices across a large network, you obviously don't have a dedicated permanent wire between every single possible pair. That would be insane.
Utterly impractical.
So you need a way to create temporary connections as needed. That's where switching comes in, right?
Absolutely. In a switched network, intermediate devices called switches dynamically connect nodes, setting up temporary paths for communication only when required.
And the two fundamental approaches are circuit switching and packet switching. What's circuit switching?
Circuit switching is like the traditional phone network, the PSTN. Before you can communicate, a dedicated physical path with reserved resources, like bandwidth, is established end-to-end between the two parties.
So you basically own that connection for the duration.
Yes. That path exists for the entire duration of the call or session, whether you're actively talking or not. It has 3 distinct phases: connection setup, data transfer, and then connection teardown. It operates at the physical layer.
The upside is guaranteed bandwidth, but the downside is the circuit is busy, tied up, even if you're silent.
Exactly. It can be inefficient for bursty data traffic where you send data intermittently. Packet switching takes a different approach.
How so?
Data is broken into smaller units called packets, and each packet carries addressing information where it's going, where it came from. Resources aren't reserved beforehand. They're allocated on demand as packets travel through the network, sharing the links.
Let's dive a bit deeper into packet switching. There are different ways it works. In a datagram network, each packet is like an independent letter sent through the postal service.
That's a really good analogy. Each packet or datagram is routed individually based on its destination address. Different packets from the same original message might actually take different paths through the network.
Which means they could arrive out of order
Oh, wait.
or even get lost.
Both are possible. So reliability and putting things back in the right order have to be handled elsewhere, usually by a higher layer protocol at the receiving end.
But there's no setup delay.
Correct. There's no setup or teardown phase, which makes it fast for sending short messages or for networks where connections are constantly changing. The internet's core packet switching works this way, operating at the network layer using IP.
But there's also the virtual circuit approach to packet switching, kind of a hybrid.
Right. This is sort of a middle ground between circuit and datagram. Like circuit switching, it does have a setup phase where a logical path is determined between sender and receiver and a teardown phase when done.
Okay.
But like datagram switching, the data is still broken into packets. The key difference from pure datagram is that once the virtual circuit path is established during setup, all packets for that particular communication follow the same predetermined path through the network.
Ah, so the path is fixed for the duration, like a circuit, but the resource allocation is still dynamic, packet by packet.
Exactly. Packets within the virtual circuit are often identified by a shorter local identifier called a virtual circuit identifier, VCI, rather than needing the full destination address looked up at every single hop after the initial setup. This is often implemented at the data link layer and used in some types of switched WANs like frame relay or ATM.
And message switching, that's mentioned too. Is that still used?
Not really for interactive communication. It's an older store and forward technique, like old telegraph systems. The entire message was stored at each intermediate switch before being forwarded to the next. Lots of delay, not suited for conversations.
Got it. Looking back at the evolution of WANs, the sources mention X.25. That sounds pretty old.
It is. X.25 was a pioneering packet-switched protocol standard, really important back in the 70s and 80s, especially for connecting over the analog phone networks at the time. It was connection-oriented, meaning it relied on virtual circuits.
And it handled reliability itself.
Yes, it provided reliable data transmission over potentially unreliable links.
Yeah.
It operated across 3 layers, defining the physical connection, the data link layer using LEPB, which had strong error control, and the packet layer for managing connections and data flow.
What were its limitations then that led to newer tech replacing it?
Well, it was slow by modern standards, typically maxing out around 64 kilobits per second, and it had quite high overhead because it did extensive error checking and flow control at multiple layers, which introduced significant latency delay.
Made sense for unreliable lines back then, maybe.
It did, but as networks got more reliable, that overhead became a bottleneck. Plus, it wasn't natively compatible with the burgeoning IP protocol and lacked the scalability and security features needed later on. So yeah, it's largely obsolete now.
Then came frame relay, which aimed to be faster.
Exactly. Frame relay was a faster packet-switched WAN technology that largely replaced X.25 in the 90s. It also used virtual circuits, but it made a key change.
What was that?
It moved the responsibility for error correction and flow control mostly to the end devices or higher protocol layers. The network switches themselves did much less processing per frame.
Ah, so stripping out that network-level error checking made the switches simpler and faster. Less work at each hop.
Precisely. Less processing per hop meant higher overall speed. It was much better suited for the bursty data traffic common from LANs and offered significantly higher speeds, T1E1 rates, and beyond.
And it had different kinds of virtual circuit.
Right. It supported both permanent virtual circuits, PVCs, which were pre-configured and always active, like a leased line, and switched virtual circuits, SVCs, which were dynamically set up and torn down on demand, more like a phone call. But frame relay 2 has mostly been superseded by IP-based networks and technologies like MPLS.
Okay, an ATM. Asynchronous transfer mode. That sounds different again.
ATM was a really ambitious technology designed from the ground up in the late 80s and 90s as a high-speed integrated network technology capable of handling voice, video, and data effectively on a single network. Its defining feature was using small, fixed-size cells.
53 bytes, right? 5 for the header, 48 for the payload. Why fixed small cells?
The idea was predictability. Small, fixed-size cells mean very low, predictable delay or latency as they pass through switches. This is crucial for real-time traffic like voice and video, where variable delays can ruin the quality.
So it was optimized for low latency and QoS.
Exactly. That cell structure, combined with strong built-in quality of service mechanisms, was key to its design goal of being a truly multi-service network. It was called asynchronous because cells are identified by logical addresses, virtual path, and circuit identifiers, VPI, VCI, allowing flexible routing not tied to fixed time slots. And it operated at very high speeds, forming the backbone for the broadband ISDN, BISDN vision.
It feels like we need a map to keep all these layers and protocols straight. That's where models like OSI and TCP/IP come in, right?
Absolutely. They provide frameworks for understanding how all the pieces fit together. The OSI reference model is a conceptual framework developed by the ISO, International Organization for Standardization, back in the 80s.
The seven-layer model.
That's the one. It breaks down network communication into 7 distinct layers, each responsible for a specific set of functions. This promotes modular design and helps ensure different vendors' equipment can interoperate.
Can you quickly walk through the layers, maybe top-down?
Sure. Layer 7, the application layer, is where user applications interact with the network, things like email, web browsing. Layer 6, presentation, handles data formatting, translation, maybe encryption or compression. Layer 5, session, manages the dialogue or session between devices, setting it up, keeping it alive, tearing it down.
Okay, halfway down.
Layer 4, transport, is crucial. It provides end-to-end delivery, either reliable like TCP or unreliable like UDP, handles segmentation of data into smaller pieces and reassembly. Layer 3, network, is about logical addressing, like IP addresses, and routing, finding the best path across the network.
Getting closer to the wire.
Layer 2, data link, handles communication within a single link or network segment. It deals with framing the data, physical addressing like MC addresses, error detection for that link, and managing access to the physical medium. And finally, layer 1, the physical layer, defines the actual physical connection, the cables, connectors, voltages, bit encoding, transmitting the raw bit stream.
That's a lot of layers. How does the TCP/IP suite compare? It's more what the internet actually uses, right?
It is. TCP/IP came earlier, developed practically for the ARPANET, the precursor to the internet. It's less of a strict theoretical model and more of an implementation suite of protocols that work together. It's typically described with fewer layers, often 5.
5. Which ones map where?
Usually it's physical, data link, network, often called the internet layer, transport, and application. The key thing is that TCP/IP doesn't strictly define its own standards for the bottom 2 layers, physical and data link. It assumes other standards like Ethernet exist there. Its application layer bundles the functions of OSI's top 3 layers: session, presentation, application.
And the core is still the network and transport layers. IP and TCP/UDP.
Absolutely. The network layer is dominated by IP Internet Protocol. It handles the logical addressing, IPv4, IPv6, and the routing of packets across potentially many interconnected networks. Critically, IP itself is connectionless and best effort. It sends the packets but doesn't guarantee delivery or order.
So it needs help for reliability.
Exactly. That's where the transport layer comes in, traditionally providing TCP and UDP. TCP, Transmission Control Protocol, is the reliable one. It's connection-oriented, meaning it establishes a connection first. It ensures packets arrive, puts them in the right order, retransmits lost ones, and manages flow control so you don't overwhelm the receiver.
Used for web, email, file transfers.
Yes,
Stuff that needs to be accurate.
precisely. UDP, User Datagram Protocol, on the other hand, is the fast, lightweight, but unreliable one. It's connectionless, just sends datagrams off without setting up a connection first. No delivery guarantees, no ordering, minimal overhead.
Good for real-time things.
Yes, like streaming video or audio, RTP often runs over UDP, online gaming, VoIP, or DNS lookups, where speed is more critical than guaranteed delivery of every single packet, or where retransmitting old data is pointless.
So quick summary. OSI is the detailed conceptual blueprint, 7 layers. TCP/IP is the practical implemented suite, often seen as 5 layers, and it's what powers the internet.
That's a good way to think about it. TCP/IP evolved organically alongside the internet and proved more practical and adaptable. And within TCP/IP, data needs different kinds of addresses at different layers to get where it's going.
Right. Physical or MSE addresses at layer 2, the data link layer.
Yep, those are the hardware addresses burned into the network interface card, NIC. They're unique locally, but change as a packet moves from one network segment or hop to the next.
Then logical or IP addresses at layer 3, the network layer.
Correct. These are the software addresses used for routing across the global internet, like your computer's IPv4 or IPv6 address. They identify the ultimate source and destination hosts and stay the same for the entire journey, end to end.
And port addresses at layer 4, transport.
a 16-bit number that identifies a specific application or process running on the destination host, like port 80 for web traffic, port 25 for email. This allows the transport layer, TCP or UDP, to direct the incoming data to the correct software application.
And finally, application-specific addresses like URLs or email addresses right at the top.
Exactly, which your computer software then translates down into the necessary lower layer IP addresses and port numbers to actually send the data out onto the network.
Let's look at some specific technologies that illustrate this evolution. ISDN, Integrated Services Digital Network. That feels like a key historical step.
It really was. ISDN was a concept and set of standards developed back in the, well, mostly the 80s, aiming to bring digital connectivity directly to homes and businesses over the existing copper phone lines. The vision was to integrate voice, data, and other services onto standard 64 kilobps digital channels.
That must have seemed revolutionary compared to slow analog modems.
Absolutely. It was a big leap towards the digital world. There was narrowband ISDN and ISDN, which offered those standard rates, and then a vision for broadband ISDN, BISDN, which aimed for much higher speeds, often involving technologies like ATM over high-speed optical links like SONET.
And the interfaces like BI and PRI became common terms.
Right. BRI, the basic rate interface, was typically for homes or small businesses. It offered two 64 kilobps bearer channels, B channels, that could carry voice or data, plus one 16 kilobps delta channel, D channel, mainly used for signaling, setting up calls.
And PRI was bigger.
PRI, the primary rate interface, was for larger connections, like connecting a business phone system, PBX, or linking telephone exchanges. It aggregated many more B channels, 23 in North America on a T1 line, 30 in Europe and elsewhere on an E1 line, along with a faster 64 kilobps D channel for signaling. The sources also detail the functional groupings, like different types of terminal equipment, TE1, TE2, and network terminations at
Right.
T1 and T2.
Okay, fast forward a bit to a widely used modern technology in core networks, MPLS multi-protocol label switching. What's the core idea there?
MPLS is interesting. It's often called a layer 2.5 technology because it operates somewhere between the traditional data link, layer 2, and network layer 3 layers. It's a key technology used by many large service providers today to manage traffic efficiently.
And its core idea is label switching instead of doing complex IP address lookups at every router.
Exactly. That's the key innovation. When a packet enters an MPLS network, the first router, called a label edge router, or LER, analyzes the packet's destination IP address, and maybe other factors, just wants to determine how it should be treated its forwarding equivalence class, or FEC.
FEC, like a group of packets going to the same place or needing the same quality.
Precisely. Then, the LER slaps a short fixed length label onto the packet. Think of it like a temporary tag or sticker.
And routers inside the MPLS network, the core routers, they just look at this label.
Yes. The core routers, called label switch routers or LSRs, don't need to perform complex, time-consuming IP route lookups based on the full destination address. They simply use the incoming label as an index into a table, the LFIB, Label Forwarding Information Base. That table quickly tells them which outgoing interface to use and, crucially, what new label to swap onto the packet before sending it on.
So it's just label lookup, swap forward, much
Right.
faster.
Much faster, especially in the high-speed core of the network. It pushes the complex routing decisions to the edges, the LERs, and keeps the core switching super fast and simple.
That sounds like it makes the core more scalable. What else does MPLS offer?
Big advantages include better support for quality of service, QoS. The label can carry priority information and powerful traffic engineering capabilities, allowing network operators to explicitly route traffic flows along specific paths, maybe to avoid congestion or meet service level agreements.
And it's multi-protocol.
Right. Because the core routers only look at the label, MPLS can technically be used to forward various network layer protocols, not just IP, although IP is the most common use case. And it can run over different kinds of underlying data link technologies like Ethernet, ATM, or even older ones like frame relay or T1 lines. The label itself, by the way, is typically 4 bytes long, containing the 20-bit label value, some bits for QoS, a stack bit, and a time-to-live TTL field.
Okay, beyond a physical paths and packet forwarding, networks need some kind of intelligence, a nervous system. That's signaling, right?
Signaling is absolutely the intelligence, the control plane of the network. It's the exchange of information needed to set up, manage, monitor, and release connections, and also to control various network operations and support features.
Like the dial tone, the ringing signal, knowing when a line is busy, actually connecting the call. all that control stuff.
All of that. It happens both between your phone and the local exchange in the subscriber loop and between exchanges across the network on the trunks.
And there's an older method, channel-associated signaling, CAS.
Right. CAS puts the signaling information in the same channel as the voice or data traffic itself. This is often called in-band signaling, where control signals might use tones within the voice frequency band, like those DTMF tones when you press keys, or older multi-frequency tones between switches. Systems like SS5 and R2 mentioned in the sources used variations of this.
What were the problems with putting signaling in the voice channel?
Several big ones. It was generally slow to set up calls because signals had to be sent sequentially. It was less efficient because the voice channel couldn't be used for conversation while signaling was happening. And crucially, speech sounds within the conversation could sometimes accidentally mimic the signaling tones.
Leading to dropped calls or features acting weirdly.
Exactly. False signaling could cause all sorts of problems.
That sounds messy. So that's where common channel signaling, CCS, came in and changed everything.
CCS was a major breakthrough. It uses a separate, dedicated channel just for signaling information, completely out of band from the channels carrying the actual voice or data.
So the signaling path is totally separate from the conversation path.
Correct. This immediately solved the interference problems. It also made call setup much, much faster because signaling messages could be exchanged quickly over this dedicated data link. And it made network trunk usage more efficient because the voice trunks weren't tied up during the signaling process. Plus, it enabled a whole raft of new services.
And SS7 is the global standard for CCS, used pretty much everywhere in the traditional phone network.
Yes, signaling system number 7, standardized by the ITU-T, became the workhorse for modern telephone networks worldwide. It's essentially a complex packet-switched data network itself, overlaid on the circuit-switched voice network. It uses specialized signaling routers called signal transfer points, STPs, to route signaling messages between exchanges and centralized databases called service control points, SCPs, that hold service logic.
And SS7 is what enables so many modern phone features we take for granted.
Absolutely. While originally designed for circuit switch call control, SS7 protocols were later adapted, using protocols like SIGTRAN, to work over IP networks as well. Its application part, known as TCAP, Transaction Capabilities Application Part, supports a huge range of functions beyond basic call setup. Things like caller ID, call forwarding, voicemail notification, toll-free 800 number services, prepaid calling cards, local number portability, LNP, keeping your number when you switch carriers, and even behind-the-scenes stuff like SMS delivery support.
Wow. The jump from older systems like SS5 to SS7 seems massive then. Much faster, more efficient, more secure, way more flexible for new services.
Huge difference. It really enabled the evolution of the modern, feature-rich telephone network.
So signaling manages the connections, setting them up and tearing them down. But the connections themselves are actually made by switching systems, the exchanges.
Correct. Switches, or telephone exchanges, are the heart of a telecommunications network. Their fundamental job is to connect incoming lines to outgoing lines, establishing a path for the call or data session. They drastically reduce the amount of wiring needed compared to, having a dedicated wire between every single pair of users.
Imagine that wiring nightmare, starting with the older electromechanical switches.
Yeah, the early ones combined mechanical moving parts with electrical relays. The Strowger step-by-step switch is a classic example, using electromechanical selectors that physically move to make connections. These were space division switches. They dedicated a physical spatial path through the switch for each call. Later came crossbar switches, a matrix of contacts.
Limited in capacity and speed, I imagine, and prone to wear.
Definitely limited, noisy, slow, and required a lot of maintenance.
Leading eventually to electronic switches, and then the big leap, stored program-controlled SPC switches.
Right. Early electronic switches used solid-state components like transistors instead of relays, but the logic was often still hardwired. The real revolution came with stored program-controlled SPC switches, first introduced commercially by Bell Labs around 1965.
Computer-controlled.
Exactly. Their functions interpreting dialed digits, finding routes, connecting lines, billing are governed by software instructions, a program stored in computer memory. This made them vastly faster, much more flexible for adding new features, just update the software, easier to manage and maintain, and enabled centralized control. Modern SPC switches often use distributed processing architectures and lots of redundancy, like hot standby or load-sharing processors, for high reliability.
And for handling digital signals, which became dominant, we have digital switching networks,
Yeah.
using space division S or time division T or combinations.
Yes. Once signals became digital, switching could also be done digitally. Digital space division switching still creates a physical path through a matrix, but using electronic crosspoints, like transistors acting as gates. However, a large single-stage space switch needs a huge number of crosspoints, NN for N lines, which gets very expensive and complex. They can also suffer from blocking not being able to connect an input to an idle output because all intermediate paths are busy.
So time division switching became important.
Very important. Time division switching works by interchanging time slots. A common technique is time slot interchange, TSI. Incoming data from different time slots is written into a digital memory and then read out in a different order, effectively swapping the time slots. This is very efficient and can be non-blocking if the memory access speed is fast enough. But a pure TSI also has practical limitations on the number of lines it can handle efficiently.
Which is why, just like with multiplexing, they started combining them, TST and STS.
Exactly. To overcome the limitations of pure space or pure time switches, especially for large exchanges, multi-stage switches combining both techniques became standard. The most common are TST, time-space-time, and STS, space-time-space.
How did it work?
In TST, an incoming signal on a specific time slot first goes through a time stage, TSI, to potentially shift it to a different time slot. Then it goes through a central space stage, a digital crossbar matrix, to switch it spatially to the correct output group. Finally, it goes through another time stage, TSI, to place it in the desired outgoing time slot. STS reverses the order. Space, time, space.
Why TST usually?
TST is generally more common and often more cost-effective for larger switches because time stages, memory, tend to be less expensive to implement per connection than space stages, cross points, for a given size and non-blocking capability. Multi-stage designs like TST significantly reduce the number of cross points needed compared to a single large space switch and can be designed to have very low blocking probability.
Makes sense. Designing these complex networks requires predicting and measuring how much they'll be used. That's traffic engineering, right? Measuring the load.
Traffic engineering is essential for designing networks that perform well without being ridiculously overbuilt and expensive. It provides the parameters to quantify network load and potential congestion. The fundamental unit you hear about is the Erlang.
E, named after the pioneer.
Yes, A.K. Erlang.
Oh.
An Erlang measures traffic intensity, essentially, how busy the network resources, like trunks or servers, are. One Erlang represents 1 hour of call occupancy within 1 hour of observation time. So if a single phone line is busy constantly for an entire hour, it carried 1 Erlang of traffic.
And it's calculated based on call arrival rate and duration.
Exactly. Traffic intensity, often denoted as A, equals the average arrival rate of calls, lambda, multiplied by the average duration of each call, T. The sources give examples. If you have 60 calls arrive in 30 minutes and the total duration of all those calls adds up to 100 minutes, the traffic intensity during that half hour was 100 minutes. 30 minutes equals 3.33 Erlangs. Traffic engineers typically focus their design on the busy hour, the hour of the day, with the highest expected traffic.
Okay, Erlangs measure the load. What about grade of service? GOS, that sounds like the user experience.
GOS is exactly that. It measures congestion from the user's perspective. It's usually defined as the proportion of calls that fail or are blocked because the network resources are busy. A GOS of 0.01 means 1% of call attempts during the busy hour are expected to fail due to congestion.
You can't have 0 GOS realistically.
Not practically. A GOS of 0 would mean you'd need enough resources like trunks for every single subscriber to be active simultaneously, which is massive overkill and uneconomical. So networks are designed to meet a target GOS, like 1% or 0.5% blocking during the busy hour.
And this leads to the difference between blocking systems and delay systems.
Yes. This relates to how the system handles calls when all resources are busy. In blocking systems, typical of traditional circuit switching, if all trunks are busy when a new call arrives, that call is blocked, it fails, it's lost, or gets a busy signal. This behavior is modeled by the Erlang-B formula, which calculates the blocking probability given the offered traffic, in Erlangs, and the number of available servers, trunks.
And delay systems, like for data.
In delay systems, more typical of message or packet switching where queues can form, if all servers, like a router's processing capacity or an output link, are busy, a new arrival, a packet doesn't get immediately rejected. Instead, it waits in a queue, experiencing delay until a server becomes free. This behavior is modeled by the Erlang-C formula, which calculates the probability that an arriving call or packet will be delayed, assuming it waits in the queue indefinitely if necessary.
And these formulas come from queuing theory, which, as you said, started with Erlang analyzing telephone traffic congestion.
Indeed. Agner Krarp Erlang's work in the early 20th century analyzing the Copenhagen telephone exchange laid the foundation for queuing theory, the mathematical study of waiting lines. It's now applied incredibly widely in telecommunications, computer networks, traffic flow, call centers, manufacturing, you name it. Erlang C specifically is based on a model where blocked calls are delayed and wait in a queue, potentially indefinitely.
Okay, we've covered a lot of core network concepts. Let's shift focus slightly to how users access broadband today and how those aggregated digital signals are transported on major links. DSL is a common access method, right? Still widely used.
Digital subscriber line, DSL, is definitely a key technology for bringing broadband internet access into homes and businesses, leveraging the existing copper-twisted pair phone lines, the local loop that runs from the customer's premises to the telephone company's central office, CO.
And the clever trick is using frequencies above the voice band.
That's the magic. Voice calls only need a narrow frequency range, typically up to about 4 kilohertz. DSL systems use much higher frequencies, often up into the megahertz range, to carry high-speed data over that same copper pair simultaneously with the regular analog phone service. XDSL refers to the whole family of technologies, ADSL, VDSL, etc.
ADSL is the asymmetric version, different speeds up and down.
Yes, asymmetric DSL is the most common type. It provides significantly higher speeds downstream from the CO to the user than upstream from the user back to the CO. This matches typical internet usage patterns where people download more than they upload.
How does it achieve that?
It often uses a modulation technique called discrete multitone, DMT. DMT essentially divides the available bandwidth on the copper line above the voice band into hundreds of narrow individual subchannels, like lots of tiny modems running in parallel. Most of these channels are allocated for downstream data, a smaller number for upstream data, and the baseband, 0 to 4 kilohertz, is left clear for the existing analog phone service, POTS.
And the setup involves a modem and a splitter at the customer's end.
Correct. At the customer site, you need an ADSL modem or router with built-in modem, and usually a splitter, a simple filter that separates the low-frequency voice signals going to the phone from the high-frequency data signals going to the modem.
And at the other end, the central office.
At the CO, the phone company has a DSLAM, a digital subscriber line access multiplexer. The DSLAM terminates the DSL connections from many subscribers, separates out the data traffic, aggregates it, and sends it onto the service provider's core data network, often using ATM or Ethernet T backhaul. It also passes the voice frequency signals through to the regular phone switch.
Okay, so that's access. What about carrying large amounts of aggregated digital signals across the network backbone? The source mentions PDH as the older way.
Plesiachronous Digital Hierarchy, PDH, was the first-generation standard for aggregating and transporting digital signals, developed back in the 60s and 70s primarily for digitizing voice calls. It was called plesiachronous because the clocks in different parts of the network weren't perfectly synchronized. They were just nominally the same frequency, but allowed to have slight variations or drift.
Like nearly synchronous.
Exactly. It built up a hierarchy by multiplexing lower speed streams, like multiple digitized voice channels, into higher speed streams, like a T1 or E1, and then multiplexing those into even higher speeds. But each multiplexer stage operated more or less independently based on its own clock.
And it had some significant drawbacks that led to its replacement.
Oh, many. A major one was the lack of a single universal global standard, especially at higher rates. North America, Europe, and Japan used different hierarchies, leading to incompatibility. Capacity was limited compared to later systems. The multiplexing and demultiplexing process was complex and inefficient.
Especially getting a single low-speed channel out.
Right. To extract a single 64 kilobp voice channel from a higher speed PDH stream, you often had to demultiplex the entire stream down, step by step, extract the channel you wanted, and then remultiplex everything else back up. Very cumbersome and required mountains of multiplexers, as they used to say. It was also primarily designed for point-to-point links and lacked sophisticated network management or built-in protection capabilities. So yes, effectively obsolete now for major transport.
which led to the development of SDH Sonnet as the synchronous successor.
Exactly. Synchronous Digital Hierarchy, SDH, the international standard, and Synchronous Optical Network, SONET, the closely related North American standard, were developed in the late 80s specifically to overcome the limitations of PDH. The key difference is implied in the name. They are based on a highly accurate, perfectly synchronized master clock across the entire network.
And the STM1 frame, or STS3 in Sonnet, is the basic building block. What's that?
Yes, the Synchronous Transport Module Level 1 ST1 frame is the fundamental unit in SDH. It's a standardized structure of bytes, 9 rows by 270 columns, that repeats precisely every 125 microseconds. This fixed duration corresponds to the sampling rate for digital voice, 8,000 samplesec, and gives STM1 a base transmission rate of 155.520 millimeps. Higher rates, STM4 at 622 millips, STM16 at 2.5 GBps, STM64 at 10 GBps, etc., are exact integer multiples of this base rate.
What are the big advantages of being synchronous and having this standard frame?
Huge advantages. First, the universal standard frame structure allows equipment from different vendors to interoperate seamlessly. Second, it enables very efficient and simple add-drop multiplexing, ADM, because everything is synchronized and the position of lower speed signals within the high-speed frame is known via pointers. You can easily insert, add, or extract, drop lower speed tributary signals directly into or out of the high-speed STM frame at intermediate nodes without having to demultiplex the entire thing.
That sounds much better than the PBH way.
Dramatically simpler, faster, and cheaper. It eliminated those mountains of back-to-back multiplexers. SDH Sonnet also supports much higher transmission capacities, enables flexible network topologies like rings and meshes, not just point-to-point, includes powerful built-in overhead for network management and monitoring, OAM&P, and very importantly, provides robust, standardized mechanisms for automatic network protection and restoration, often using self-healing rings that can automatically reroute traffic within milliseconds if a fiber link is cut. It was a massive leap forward in optical network transport capability and reliability.
Okay, just touching briefly on a few related areas the sources mentioned before we get to NGN and VoIP. Radar, navigation systems, and GIS. How do they fit in?
Well, radar, radio detection and ranging, is related in that it uses electromagnetic waves, specifically radio waves, to detect objects, determine their distance by measuring the time delay of the reflected echo, and sometimes their speed, using the Doppler effect. Navigation systems help us determine position, speed, and direction. They've evolved from celestial navigation and orienteering to radio navigation, inertial systems, and now predominantly satellite-based systems like GPS, Global Positioning System, GLONASS, or Galileo.
And GIS, Geographic Information Systems.
GIS are powerful software and hardware systems used to capture, store, manage, analyze, and visualize all kinds of data that is tied to geographic locations on Earth. Think of it as combining maps with databases. In telecom, GIS is incredibly important for planning network infrastructure, like figuring out the best routes for fiber optic cables, where to place cell towers for optimal coverage, managing assets, and visualizing service areas. It connects the where with the what.
Makes sense. Okay, which brings us nicely to the modern vision of telecommunications, the next generation network, or NGN, and its key application, voice over IP, VoIP. What's the big idea behind NGN?
NGN represents a fundamental shift in telecommunications network architecture. The goal is to move away from having multiple separate, vertically integrated, service-specific networks like the traditional circuit-switched phone network, a separate data network, maybe a separate cable TV network, towards a single, unified, packet-based transport network capable of carrying all types of services, voice, data, video, multimedia together.
So everything becomes packets running over one core network, typically IP, an all-IP network.
Exactly. That's the usual foundation. Key characteristics of NGN include being packet-based, designed to support multiple diverse services with guaranteed quality of service, QoS, having a clear separation between the underlying transport layer and the service control layers, service transport independence, a layered architecture with open interfaces between layers, supporting unrestricted access for users, and enabling generalized mobility. It's generally seen as an evolution from legacy networks, not a sudden overnight replacement.
And this layered architecture involves access, transport core, control, and service layers.
Right. The access layer provides the connection for various types of user devices or legacy networks via access gateways, AGs. The transport or core layer is responsible for transporting the packets across the network. It's usually based on IP and often uses MPLS for traffic management and includes routers and optical transport systems. It also needs gateways, like trunking gateways, TGs, or media gateways, MGs, to interwork with the legacy PSTN.
Then the control layer provides the brains.
Yes, the control layer handles the signaling, call setup, routing logic, charging, authentication, QoS control, and overall session management. This is often managed by devices called soft switches, media gateway controllers, MGCs, or call agents. They control the gateways in the transport layer.
And finally, the service layer.
The service layer is where the actual applications and enhanced services reside, running on application servers. This could be anything from basic telephony features to advanced multimedia services, video conferencing, unified communications, or even third-party applications accessed via open interfaces like APIs. Key network elements enabling this include those gateways, AG, TGMG, SG for signaling, and the crucial soft switch MGC.
And VoIP is the prime example of a service running on this packet-based NGN infrastructure. Voice just becomes another application.
Voice over IP, also called IP telephony or internet telephony, is exactly that. It's simply the transmission of voice communication and multimedia sessions over IP-based packet switch networks, rather than establishing a dedicated end-to-end circuit like in the traditional PSTN.
So fundamentally different from the old way.
Completely different underlying mechanism. Instead of dedicated TDM circuits switched based on SS7 signaling, VoIP digitizes the voice, compresses it, breaks it into IP packets, and sends those packets across the IP network, typically using protocols optimized for real-time media.
What protocols are key for VoIP?
You need protocols for two main things: carrying the actual media, voice video packets, and signaling, setting up, managing, tearing down the calls. For media transport, RTP, Real-Time Transport Protocol, is standard. RTP usually runs on top of UDP for low overhead and speed and provides features like sequence numbers and timestamps to help reconstruct the audio-video stream at the receiver, even if packets arrive slightly out of order or with jitter. SRTP is the secure version.
When for signaling?
Several signaling protocols exist, but SIP, Session Initiation Protocol, has become the most widely adopted standard for initiating, modifying, and terminating interactive user sessions involving multimedia elements like voice, video, and messaging. H323 is an older, more complex standard that's still around, and MGCP, Media Gateway Control Protocol, is used for controlling gateways from a central controller. RTSP, Real-Time Streaming Protocol, is also relevant for controlling streaming media servers.
What makes VoIP appealing? Why the big shift?
Several factors. Cost is a big one. Sending voice packets over shared data networks is often significantly cheaper than using dedicated circuit switch lines, especially for long-distance and international calls. Flexibility and portability are others. You can often use your VoIP service anywhere you have a decent internet connection. And it enables rich media integration, easily combining voice with video calling, instant messaging, presence information, file sharing, all within the same communication platform.
Are there downsides or challenges?
Definitely. VoIP quality is highly dependent on the underlying IP network's performance. You need sufficient bandwidth, low latency, and low packet loss for good quality. Congestion or poor internet connectivity can lead to dropouts, echoes, or delays. Security can also be a concern if the connections aren't properly encrypted or firewalls aren't configured correctly, making it potentially vulnerable to eavesdropping or denial of service attacks. The source provides a helpful table comparing traditional PSTN and VoIP across these points.
And the IP-PSTN platform, that's just about connecting these two worlds.
Yes, that term refers to the necessary infrastructure, particularly the gateways, media gateways and signaling gateways, and interworking functions, needed to allow seamless communication between the new IP-based NGN VoIP networks and the vast existing legacy PSTN infrastructure during the long transition period where both coexist.
Makes sense. And finally, one more acronym. Intelligent Networks, or INN. What was that about?
The Intelligent Network, IN, was a network architecture standardized by the ITU-T in the Q1200 series, mainly in the 90s. Its key driving goal was to separate the complex service logic for value-added services away from the core switching systems themselves and place it into centralized databases, SCPs, accessible via the SS7 signaling network.
Why do that?
The motivation was speed and flexibility. Before IN, adding any new service often required complex, slow, and expensive software updates to every single switch in the network. IN aimed to make service creation and deployment much faster and independent of the underlying switch vendors. Service logic resided in the SCP, and switches would query the SCP via SS7 when they encountered a call needing special handling, like a toll-free number.
So many of the advanced calling features we saw emerge in the 90s were enabled by IN.
Exactly. Things like toll-free 800-888 numbers, premium rate 900 numbers, virtual private networks, VPNs for voice, universal personal numbers, prepaid calling cards, call forwarding variations, voicemail integration, local number portability. Many of these relied heavily on the IN architecture and its interaction with SS7. It was a bridge towards more flexible service platforms like those in NGN.
Wow. We have really journeyed through the layers and the history of telecommunications today. It's quite a landscape.
We really have. We took your sources and navigated from, the physical transport of signals and the impairments they face, like noise and echo,
Through how capacity is shared using techniques like FDM and TDM multiplexing.
how networks are structured, categorized by size, like LAN, MAN, WAN, and the different ways they connect devices,
The fundamental principles of circuit switching versus packet switching, including datagrams and virtual circuits.
the architectural models like OSI and TCP/IP that help us make sense of it all, and the key protocols like IP, TCP, UDP.
The evolution of WAN technologies from X.25 to frame relay to ATM, and the crucial shift in digital transport from PDH to the much more capable SD8 sonnet.
We touch on the operational intelligence with signaling systems, comparing CAs to CCS and the powerful SS7, and how switching evolved from electromechanical to SBC and digital TST networks.
How network load is measured using traffic engineering concepts like Erlangs and GOS based on queuing theory.
Looked at access with DSL, and finally, the modern shift towards the converged next-generation network, NGN, and the rise of voice over IP.
Yeah, our goal was really to distill the key knowledge from that material, providing you with insights and maybe some shortcuts into this incredibly complex interconnected world.
Hopefully you found several aha moments along the way, connecting some of those dots.
Thinking about this incredible journey of innovation, from simple copper wires barely carrying one conversation at a time to a global network of networks where voice, data, video are all just packets flowing together.
It's been constant evolution, hasn't it? Driven by the relentless need for more capacity, more efficiency, more services, lower cost.
It really makes you wonder, where does it go next?
That's the big question.
Exactly. Considering all these fundamental shifts we've covered from circuit to packet, from fixed hierarchies like PDH to flexible ones like SDH-MPLS, from in-band signaling to powerful out-band systems like SS7, from service-specific networks to converged NGN, what's the next truly fundamental shift on the horizon for telecommunications? And maybe more importantly, how does understanding this rich history prepare us to anticipate and navigate whatever comes next?
That is a fascinating question to sit with. The pace certainly isn't slowing down.
To keep exploring that question, thanks for joining us on this deep dive today.